All right. All right. Good afternoon or good morning, everybody. Welcome to the last seminar of the year. Today we have Chris Fewster. He's going to talk to us about recent developments in the theory of quantum measurements in quantum field theory. And it's a topic that has been discussed a lot in quantum foundations in this time. So I'm very excited about this seminar. And just as a reminder of the format, there will be plenty of time for discussion and question and answer at the end of the seminar. So Chris will give maybe 30-40 minute presentation. And please feel free to unmute yourself to ask a quick clarifying question, but let's keep more difficult or challenging questions for the discussion time. And with this, I give you the microphone. Chris.
Okay, thank you very much indeed, Andrea. So this is a talk about measurement in quantum field theory, and I've titled it Problems and Solutions, and you'll have to decide for yourselves whether the problems are real problems and the solutions are real solutions, but we'll take it from there. So this is based on work that I started with Rainer Fersch a few years ago now in this paper that's in CMP, and then further developed with my colleague at that time, Henning Bostelmann, and our student Maximilian Rupp. And this year, Rainer and I wrote a sort of encyclopedia entry on measurement in quantum field theory, which summarizes what I'm going to tell you today and some other things as well. Okay, so starting with the problem, I think probably everybody on this call or has probably either been to a course in quantum theory or taught a course in quantum theory or read a book on quantum theory where the following things were said: that observables are Hermitian operators, that when a Hermitian operator is measured, the result is one of the eigenvalues, and that the state vector collapses instantaneously to the corresponding eigenvector. And that's a pretty common way of presenting elementary quantum mechanics. And the great thing about this is that pretty well everybody will agree that this is a presentation of elementary quantum mechanics, and pretty well every part of it is wrong for one reason or another. So you can criticize this on mathematical grounds and physical grounds and conceptual grounds. But what I'm going to focus on today is just one part of it, which is that this collapse rule is clearly incompatible with relativity and quantum field theory. And it always amuses me that when we teach undergraduates, they go along to the special relativity course and they hear that there's no such thing as absolute simultaneity, and they all nod and take notes and pass the exam and so on. And then in the next lecture, they go to quantum mechanics and they're told that there's instantaneous collapse of the wave function, and they nod and take notes and maybe pass the exam. But somehow the huge disconnection between these two statements seems to go unnoticed. But of course, it's well known that there is a problem with collapse in quantum field theory. And this really creates a problem if you try to extend the rules of quantum mechanical measurement, particularly if you start with this sort of naive presentation up here. If you try to extend that to quantum field theory, you run into trouble. And in fact, I think this is now a well-known quote. Ehrman and Valente described it as a major scandal in the foundations of quantum physics that there was no agreed understanding of the rules of measurement for quantum fields of the sort that there is more or less for quantum mechanics. And this is born of the following observations: that when you go to the literature on quantum field theory, you will find very little about measurement. And conversely, when you go to the literature on quantum measurement, you find relatively little about quantum field theory. And the literature that there is more problems than solutions. So that is the sort of status report of where things got to, well, say up to about 5-10 years ago. So I'm going to give you now a quick reminder of one of the problems, which is this famous impossible measurement scenario that Raphael Sorkin came up with in 1993. And in fact, in that paper, he starts from saying the observation that nobody has come up with good rules for quantum for measurement in quantum field theory, and says it shouldn't be hard to do this. and then he writes down some obvious seeming rules, and then immediately points out that there's a problem with it. And the problem is the following. He says, well, imagine you've got three regions, A, B, and C, and A and C are going to have no causal connection between them. Okay, so here's a light ray and it misses C, for example. But the future of Alice's region actually does intersect part of Bob's region, and the past of Charlie's region, if we like, intersects Bob's region. Okay, so there can be causal connections between A and B and C, but none between A and C. And here it's critical, of course, that we're talking about open sets. Okay, if we're talked about point-like observables or point-like observers, we wouldn't get this problem cropping up. But we work with extended regions in quantum field theory. So what Sorkin did was to say, well, Alice is going to make a non-selective measurement of a quantum field theory, of some observable of a quantum field. Bob is definitely going to make, sorry, I think I said this the wrong way around. Alice chooses whether or not to make a non-selective measurement. Bob is definitely going to make a non-selective measurement. And the question is whether Charlie can tell whether or not Alice did or did not make her measurement. And in Sorkin's example, he writes down what he claims is a fairly typical measurement that Bob makes that allows Charlie to determine whether Alice did or did not make her measurement. So, of course, he is not advocating superluminal communication. Rather, the point is that if something that Bob apparently does leads to superluminal communication, then this had better be an impossible measurement. So that's the idea of the impossible measurements, these things that would apparently allow superluminal communication between Alice and Charlie. So then Sorkin says, well, there didn't seem to be anything particularly special about the observable or the measurement that Bob made. And since this is typical, you now are left with a big problem because it's not clear in quantum field theory which observables you can safely measure, okay, and which are going to lead to these superluminal communication problems. And so he drew the conclusion that, in fact, maybe quantum field theory does not have any definite measurement theory. And you just have to resort to case-by-case analyses to try to work out what's allowed and what is not. So that is the impossible measurement scenario, and we will come back to that later in the talk. And I'm moving quite swiftly now towards the cure, because I'm trying to keep this to be a reasonably short talk. What Rainer Fesch and I decided was that in some ways, we did not want to just construct rules out of thin air, because this is something that's been tried and, as we've seen, leads to some problems. But what one can do instead is be a little bit more systematic and model the measurement process. And this, of course, is what goes on in a theory of quantum measurement theory. And we wanted to combine those insights with those of modern quantum field theory in curved spacetimes. So as an example of the literature on quantum measurement, I pick out this book by my late colleague Paul Bush and his co-authors on quantum measurement. This is a very nice theory. It gives you a very full explanation of the measurement chain in quantum mechanics, how you measure a system by letting it interact with the probe, and then you measure the probe and you learn about the system. But this whole theory has very little attention to quantum fields. Okay, so that's one side of the equation. On the other hand, algebraic quantum field theory gives you a very nice conceptual framework for doing quantum fields, for studying quantum field theory. And it talks about observables and states and so on. But remarkably, it has little attention to measurement. So on the one hand, so there's just this chasm between these two worlds that really ought to have talked to each other a long time ago. And our idea was to try to bring the insights from the two sides together. So this is how we did it. I'm going to tell you actually first a little bit about quantum field theory in the algebraic approach. And the idea is that quantum field theory is described very generally in terms of a star algebra, A of M, if M is the space-time. So this algebra has got a unit, and we can, of course, because it's an algebra, form linear combinations, products. It's a star algebra, so we can form a star, and there's a unit. And we can form all sorts of combinations like that. And we also will have subalgebras, which are indexed by suitable open regions n within M. Okay, and if we set n equals m, we should get the whole algebra back. That's the starting assumption. A typical element that we'd find in one of these local algebras would be a smeared field. So if phi is a quantum field and you integrate it against some test function that vanishes outside n, that is the sort of object you would expect to find in a local algebra. Okay, so that gives you an idea of what these local algebras are about. So this is quite a general framework, and it has to be constrained a bit by some assumptions. Some of them are very, very obvious. So if one of these regions is contained in another, you would expect that the algebra associated with the smaller region is contained within the algebra associated with the larger. And this is called isotony. One that's not maybe immediately obvious is the so-called time slice axiom. And that says that if a region N is big enough that it contains a Cauchy surface for the whole space-time, then the algebra of its algebra associated with N is already the whole algebra, A of M. And in some ways, this encodes at an abstract level the idea that there's some sort of dynamical law, that if you know what's happening in the neighborhood of a Cauchy surface, then you know everything there is to know in the whole space-time. So this, if you like, encodes the presence of a dynamical law. And depending on what you're doing, there may be other assumptions that get added in. And I'm not going to be explicit about all of the assumptions in this talk, but there aren't very many more than I've written down here. Now, what's the interpretation? Well, a self-adjoint element, in other words, A that's equal to A star, this should be interpreted as an observable, localizable in N, if it belongs to one of these local algebras AMN. It's quite clear that an observable can be localized in many different regions. If we just think about this isotony axiom, if we can be localized in region N1, then obviously we can be localized in any larger region N2. And if we can be localized anywhere in the space-time, then we can be localized in a neighborhood of any Cauchy surface. So it's not that a given observable has a specific localization associated with it. Rather, given any observable, it may be localizable or not in one of many different regions. So this feels a little bit different from Hilbert space, quantum mechanics or quantum theory, and it's slightly different in some ways. We have a different notion of state, which is here a state is a linear map from an algebra to the complex numbers with the property that it acts on the unit to give you 1, and it acts on obviously positive elements to give you an obviously positive answer. And the idea is that omega of A is going to be the expectation value for measurements of A in the state omega. And probably you will have heard of something called the GNS construction. And if you have a state and one of these algebras, you can find a Hilbert space representation in which everything will look exactly as it normally does in quantum mechanics, if you like. Okay, so you can get back to the Hilbert space framework from here. But I'm not actually going to need Hilbert spaces in anything that follows. Okay, so that's a sort of quick start on algebraic quantum field theory. I just want to make one last point, which is that we have not assumed any particular Lagrangian in what I've said here. This is supposed to be a framework that would apply to any quantum field theory worthy of the name. Okay, so I get to do all quantum field theories, all possible quantum field theories in one go, if you like. So moving to the idea for describing measurement, we're going to take the view that we're interested in understanding a particular quantum field theory, which we'll call the system. And we're going to measure it by letting it interact with another quantum field theory, which will be called the probe. So A is for the system and B is for the probe. And we will work on any globally hyperbolic spacetime. So these are curved spacetimes that have Cauchy surfaces. So it's a pretty general class of curved spacetime, not just Minkowski. And just to remind you, A of M is the algebra of all system observables, and then AMN is the subalgebra that's localizable in the region N. And given the system and probe, we can, of course, put them together in a somewhat boring way. We can just take a tensor product of the system algebras and the probe algebras, and we will call that the uncoupled combination of A and B. And so in this way, given A and B, we get a new theory, which we'll call U, and that's this boring combination of system and probe. But the measurement we need will be described using a different quantum field theory, which we'll call the coupled combination. And all we're going to assume is that there is some bounded coupling region, K, in space-time, and outside which, or outside more precisely its causal hull, C and U coincide. So I didn't tell you anything about what the theory A was, or the theory B, or the theory C. They're quantum field theories, and all we're assuming is that C and U coincide outside K. So as to what the precise coupling is inside K, I don't know. And all I ask is that it should be describable by a quantum field theory. So that's the assumption. Now, this can all be turned into precise mathematics. And when you combine it with what we know about Lorentzian geometry and the axioms of algebraic quantum field theory, you're led very quickly to the existence of isomorphisms between the uncoupled algebra for the whole space-time and the coupled algebra for the whole space-time. And in fact, there are two natural isomorphisms that turn up. One for the early times and one for the late times. And these come about simply because at early times, you're outside the causal hull of K, and therefore C and U should coincide. And at early times, there'll be a Cauchy surface. So you can learn everything about both the uncoupled and the coupled theory at early times. On the other hand, at late times, you're also outside the causal hull of K, and there's also a Cauchy surface up there somewhere, or many of them actually. So again, there will be an isomorphism between the uncoupled and the coupled theory. So you can identify them at early times or late times. And there's a nice commutative diagram that I can send you to if anybody wants to actually see the details of this. But I think I'll leave that for if there are detailed questions later on. But given these two isomorphisms, the early and late time identifications, we can, of course, put them together. So at late times, I hop across from uncoupled to coupled, and then I follow that by the inverse of the early time identification. So overall, I've got an isomorphism from the uncoupled theory to itself. And what that is doing, that isomorphism, it's a scattering map. And scattering, like any scattering map, it's a comparison of two dynamics: the dynamics of the uncoupled theory and the dynamics of the coupled theory. So all of that gets encoded in a particular isomorphism, algebra automorphism even, of this uncoupled algebra. Okay, so all of the information about the coupling goes into theta. Okay, so that's what that's the starting point. It leads to the idea that we have these identifications and a scattering map. And now we can come to the way measurements are described. So as ever with a measurement, we prepare early and we measure late. And we're also going to use these maps, Tor, plus, and minus, as a sort of dictionary. We're going to use them to translate statements about the uncoupled dynamics into the physical coupled one. Okay, because when we make the experiment, when we perform the experiment, we're using the coupled theory, but we are going to talk about it in language appropriate to the uncoupled system. Okay, this is an important point. So, for example, we will say things like, we prepare the system and probe independently at early times. And it's clear what we mean in the uncoupled theory. We just take a tensor product of the two states. So so omega is the system state and sigma is the probe state. Then this is the preparation that reflects the system and probe being independently prepared at early times. But the actual experiment is on the coupled theory, and we can carry across this state to its image on the coupled theory by using the identification at early times. And because of the direction of all the maps, we have to actually put the inverse of the early time identification in here. So this is one way of translating from the uncoupled to coupled language. The other comes when we talk about the measurement, because we will have an observable of the probe in mind. And again, in the uncoupled theory, it's quite clear what we mean. We just tensor it with the unit. And to translate that into an observable of the coupled theory, of course, we use the late time identification, because that's where we're going to measure the probe. So we have a state and we have an observable. So of course we can compute the expected measurement outcome. So this will be actually the value we would get if we repeated this many, many times and so on, the expectation value of this observable in the coupled theory using this state. But now we want to go back and get a description of the experiment at the level of the system alone. And what that means is that we're looking for an observable of the system whose expectation value in the original system state matches the expectation value of the actual experiment that we perform. Okay, so we're going to do this by matching expectation values. So if we can find an observable that has that property, we'll call it the induced observable. And well, I've denoted it for better or worse with this var epsilon sub sigma. Just to remind you, sigma is the state that we use to prepare the probe, and B is the observable on the probe that we were measuring. Okay, so this gives you a sort of a way of learning about the system by measuring the probe. So I think I say that a little bit more here. So yes, this is the system observable you learn by measuring B on the probe. You can actually find explicit formulae for this induced observable, and it can be written very simply. So here is our probe observable tensored with the unit. Here is the scattering map, and this eta sub sigma, this is essentially a partial trace where we use, again, we use that system preparation state, sigma, to do that partial tracing on of the probe theory, to trace that out. Beg your pardon. And this is quite a simple formula. and it can be computed in specific models. So there are a number of particular models based on free fields where you can really compute and calculate with these induced system observables. But you can also prove things in general about the induced observables. In particular, you can show that they are localizable in any neighborhood, any suitable neighborhood of the coupling region. And in fact, this is the question that Rainer and I set out to answer. Okay, that's why we did this. We wanted to know, what is it you learn about one quantum field theory, in particular, where are the observables that you learn about localized when you have some sort of measurement interaction. So that's why we did this, to answer this question. And we really weren't too sure what we would find, but in the end, it is the nicest possible answer, namely that the observables you learn about are those that are localized where the coupling was. Okay. So
sorry for the interruption.
Sure.
Just a clarification. So these are observables of the uncoupled theory.
Of the system theory, yes.
Of the system theory in the uncoupled version.
Yeah.
Okay, yes. And right. By suitable, what do you mean?
So they're connected, open, causally convex.
Okay. Nice.
Okay, so I mean, the reason is the reason for this collection of adjectives is that K was assumed to be compact, and we only allow local algebras to be indexed by open regions. Okay, so it can't be in K because K doesn't have an algebra associated with it. So it's the next best thing, which is anything that's allowed that contains K. That's what's going on here. Right, so it's right. So that's one thing you can prove. Another thing that you might wonder is, well, what happens if I measure a probe observable that can be localized space-like to K? Now, an observable in that region should not know that there's any coupling there at all. Should be completely ignorant of that. However, if you put it through this sausage machine, you can see what comes out. And what comes out is a multiple of the unit. In other words, it's a trivial observable. You can't learn anything from it. So this protects your ignorance. You should not learn anything about the system by measuring such an observable, and indeed you do not learn anything about the system. So that's good. And it's something that comes out rather than being assumed. Another thing that will be actually probably very much expected by people who know about these things is that the induced observables are typically unsharp. So even if you could measure a projector on the system, on the probe, the induced observable in the system will be not a projector anymore. It'll be an effect, namely a positive operator trapped between 0 and the unit. Okay, so that is quite common in quantum measurement discussions. So that's well, some of what you can say about the induced system observables, and I think now we're turning to indeed the question about states. So we have to face the question, how are we going to update a state? And to answer that, I think the best way is to think, well, what did we want the state for anyway? What is the role of a state in quantum theory? In fact, in any physical theory. And certainly here, the role of a state is to compute probabilities for measurement outcomes. So let's suppose that we have one of these effects. That's a yes-no observable. The probability of success is given by the expectation value of B in the state we're interested in. So probability of success is given by this expectation value. Now, let's suppose that we measure some effect and we're successful. We now wish to go on and make further experiments. And so the role of the post-measurement state really is one of computing conditional probabilities now for the subsequent outcomes conditioned on the measurement that we've already made. So here let's suppose that we measured a yes-no observable A, and we now wish to predict probabilities for success in some subsequent yes-no observable B. Well, we are looking to see if we can find a state that will give us the conditional probability. Okay, so notice that here we have a probability and here we have a conditional probability. And I think this is quite an important point, and come to in a second. But also what's important is that we can compute this updated state. So there's a formula for it. When A is an effect of the probe coupled to the system, and we can do this when we're measuring with selection and also when we're measuring without selection. And the important point is that you do not need to assume that the state actually changes as a physical process in space-time or anything like that. The viewpoint here is that it's not the physical state that's changed, it's the question. Originally, we were asking about the probability of some yes-no observable giving us a yes. And then after the measurement, we want the conditional probability of some other observable conditioned on the fact that we got success in the first one. That's what changed, the question, not in the same way, not the traditional view of the collapsing wave function. Okay, so I really prefer to think of this as bookkeeping. The update rule is about doing the bookkeeping to allow you to compute a conditional probability given the additional knowledge from the A measurement. That is the viewpoint that seems most consistent with what's going on here. This is not a new viewpoint. You'll find it in the book of Powell Bush, and it goes back to Davies and Lewis, I think. I think maybe I'm insisting on it a little bit more strongly than people have in the past. But anyway, this is not an entirely new viewpoint by any means. So, in fact, here is the formula for the updated state. And you can see this is with selection on a yes-no observable A. And it's very simple. Here is, so if we're now trying to compute the expectation value of some observable C in the updated state, well, there's C, there's our yes-no observable, there's the scattering map that we were using in the interaction when we measured A, there's the preparation state for the A measurement, and here is our original system state. And of course, the denominator here is just some normalizing factor to make sure it's normalized to be a state. And what's very nice is if we measure without selection, then we get a formula in which A is completely absent. We have the scattering map and the preparation state, but what happens, of course, is we weight, we form a convex combination of these guys weighted by the success probabilities, which are the denominators. So they cancel out, and in fact, we're left with A and 1 minus A, and so they sum to give us the unit. So you get a very simple formula for the non-selective update. And then there are theorems one can prove. If you have updates at space-like separation, you might think, well, what happens, which one should I do first? And the answer is it doesn't matter. You can update for A and then B, or B and then A, or frankly, you can think of both of them as a single overall measurement and update for that. And you get the same in all cases. Something else I like is what I call the principle of blissful ignorance. If you take an observable that's localizable space-like to the coupling region, then there is no change in the expectation value when you make a non-selective update using measurement of A. So you do not know. You don't notice any change in that situation. And then the other side of the coin here is what I call unspooky action at a distance. You can ask, well, what about selective updates? When do I see any difference between the update and the original state? And the statement is, well, these expectation values are the same if and only if there is no correlation between the observable B and the induced system observable coming from A in our original state. So turning that around, what we can say is that any difference between these two expectation values can be traced to correlation, by which I mean including those of entanglement and so on. But there's no surprise that if there are correlations between two different observables in the original state, and you measure one of these observables and get a measurement outcome, of course you would expect that your predictions for the measurement of the other one will change. So these are all properties that can be proved from the update rule. And now I think we can come to the impossible measurements scenario. So there's going to be a bit of a sketch, but remember the situation is that we have Alice, Bob, and Charlie. Alice chooses whether to make a non-selective measurement. Bob is definitely going to make a non-selective measurement. And the question is, can Charlie tell whether Alice did or did not make her measurement, which can be written in symbols by this equation or inequality. The question is, if there is an inequality here, then Charlie can tell. Okay, here we have the update when only Bob makes the measurement, and here we have the update where both Alice and Bob make their measurement. So we can analyze this using our framework, and with a little bit of thinking about the way that scattering maps work, and things I haven't quite told you about, but which come out of the formalism with some thought, you discover that if we take the scattering map for Bob's measurement and we apply it to Charlie's observable, now we have to tensor in, of course, Alice's unit and Bob's unit, this will give you something that is localizable in a region like this, N. And the point about N is that it is space-like from A. And because of that, it turns out you can prove that the non-selective update by both Alice and Bob gives you the same expectation of Charlie's observable as the non-selective update for Bob's observable alone. This is an example of blissful ignorance, okay, because effectively you're trying to measure something space-like separated from the Alice region. So it is a theorem. Charlie can't determine whether Alice measures, which means that there are no impossible measurements in our framework. So that's good. Of course, underlying this is the assumption that all of the theories I've been talking about are quantum field theories, and that means they've got locality built in. Turning it around, if you want to perform an impossible measurement, you'll need some impossible apparatus, something that does not respect locality. So that goes some way to resolving the Sorkin problem, but it isn't actually the end of the story, because we can now see that, well, two things. We can see that the problematic aspect was that Sorkin's update rule was not actually as good an update as he thought. He'd taken a typical element, a unitary element in a local algebra, and said, well, let's just update the state using that. And so what our analysis brings out is that, well, not all elements of a local algebra induce a local update. And this is something that is not peculiar to quantum field theory. There's a recent paper by Rainer Fersch and Albert Much where they show that you can do this even in classical field theories. Local algebras can contain elements which produce non-local updates. This is not surprising. If you imagine yourself writing down an interaction Lagrangian, you would always, because you're trained to do it, write down a local interaction term. But we're all aware that there are plenty of other things you could write down very easily that would give you non-local interactions. And in the same way, in the local algebras, there are all sorts of things that could be measured locally, but which should not be regarded as representing something that could be implemented by local dynamics. So that's somehow how we understand what went wrong in the Sorkin analysis. But as I said, there's a little bit more to it, because it's one thing to say that there are no impossible measurements, but you then have to answer the question, well, what can you measure? Okay, because maybe there are not very many interesting things you could measure. Admittedly, you can't measure anything impossible, but you really want to know that you can measure plenty of interesting things. And this was something that I looked at with Ian Jubb and Maximilian Rupp. And what we showed was that at least in one model, you could get at a dense subset of all observables. So, something I'm working on at the moment is actually about improving that to say absolutely all of them on the nose. Okay, so what's out there is this asymptotic result, but I believe I can do rather better than that. So with that, I would say that all of the problematic aspects of impossible measurements are resolved. We have a framework that doesn't give you any impossible measurements, but is rich enough to give you all of the observables that you'd like to have. And I think that brings me to the end. Excuse me. So what I hope I've shown you is that there now is a consistent system of measurement schemes and update rules in quantum field theory. It is completely consistent with relativity and curved spacetimes. As far as we've seen, we haven't found any problems with it. You can have multiple observers. I didn't say very much about that, but you can. Ignorance is protected in the right places, and we have resolved the problems with impossible measurements. So it is effectively comprehensive as well as consistent. And as a sideline, this actually also clarifies a little bit the interpretation of the local algebras in AQFT, that the typical algebra elements really should be thought of as things you could observe rather than things you can do. Okay, remember, this is the point. Not all local elements, not all unitary elements in a local algebra should be thought of as giving you local dynamics, but they are all, or at least all the self-adjoint ones, are things you can observe. And the last point that I'd really like to emphasize is that in deriving this framework, we tried to put as little as possible in and get as much as possible out of quantum field theory itself. So we tried to go with the grain of the theory, work from minimal and general assumptions, and then see how does quantum field theory itself wish to describe measurement. And that's hopefully what we have brought out. So with that, I'll thank you for your attention.
Thank you very much, Chris, for the clear presentation. Very interesting. We can open the field to questions. If you want, you can raise your hand using the Zoom interface. Let's see if somebody. Yes, so Lucian Hardy has a question.
Well, thank you for the talk. It was beautifully clear. At least I hope so. Maybe my question will be on item. This idea that when you condition, you're merely just changing the bookkeeping. There's potentially some tension between that idea and a violation of Bell inequalities. Have you looked at violations of Bell inequalities in this kind of context?
The truthful answer is no, but it's next on the list. It's one of the things that's next on the list is to understand that precisely. There should not be any conflict at all.
You must have some sense of how it would go.
Yes, I do.
Okay, okay.
So I mean, the stage I'm at is actually trying to get good models of particle detectors. That's the stage. And when I've got one particle detector, then I can easily have two, and then I'm in business.
Okay.
But I genuinely do not believe there will be any problem revealed at this point. As I say, the change in expectation values is to do with correlations, but those correlations can be the effect of entanglement. This is not just classical statistical correlation. It is correlation, but the nature of that correlation is not specified.
Okay, and then since there are no hands raised currently, one more question. So you said, I think it was slide 15, maybe 14, that the key assumption was this locality. Key assumption: the probes and the coupling are described by physics reflecting locality. So that assumption must be built into the way you set up the field theory.
Yes.
I'm not sure if you explained how it's built in. Could you perhaps explain?
Okay, yeah. Maybe I can go back to if I go to the quick start on quantum, algebraic quantum field theory. So if we look at these axioms here, so isotony, this is relates to locality. It says that the way that these algebras are indexed by local regions respects inclusion. So that's the first thing. Mm-hmm. The second is this time slice, and this also comes in a more localized version, that if in fact N1 had was big enough to contain a Cauchy surface of N2, then these would actually be equal. I only stated the global version of time slice here. Okay. There is also going to be, so one of the other ones would be Einstein causality, which says that if N1 and N2 are space-like separated, then these regions would commute element-wise. Okay. And so because of this, the theory knows about the causal structure of space-time. It's built in through the algebraic relations between the local algebras and the way that the conditions on the local algebras reflect causal structure of space-time. So these conditions look quite innocent, and I claim they are quite innocent, but they have quite far-reaching consequences.
Okay, I see that now. Good. Thank you.
There is a question by Martino Trassinelli, who is dealing also with his kids, so he can't unmute himself. But he's asking about, I guess it's a general question about algebraic quantum field theory. How to treat continuous interacting fields in these formalisms, like an atomic bound system, for example, and how do you probe such systems?
So was the question about continuous observation?
I think it's about I think it's more about having the interaction region not necessarily being bounded. Maybe.
Oh, okay, yeah, okay. So this is something that I have been working on. So we have a paper that's close to completion, and the situation is you do not need to assume that the interaction is compact. In fact, you could say I've actually made the framework more restrictive than I need to, and you can certainly say, well, this K could be allowed to stretch over a Cauchy surface, and that's actually then a looser framework than the one that I've written down. I originally wanted to write it down so experiments take place in bounded regions of space-time. That was the starting idea, but for sure you can have it spread over a Cauchy surface. And then the interesting question is, well, supposing you can't totally control what the coupling is outside, some particular region, what can you do? And the fact is, well, if you've controlled it in a big enough region, then you can learn about you can learn about things essentially in the Cauchy development of this region where you do have absolute control. So this is essentially the answer to the problem about tails to the interaction region. There's no great problem with that, and provided you can control things in a big enough region, then you can do the experiment in a suitable region. Or putting it another way around, if you know what region you want to measure observables in, then you know how big a region of space-time you need to control.
And by control, what do you mean?
so that where you actually are specifying the coupling. Okay, so you could imagine that take two different coupled combinations of A and B, and maybe imagine now that this is determined by a Lagrangian who's got two interaction terms. Because it's localized, that means there's probably some cutoff in front of the interaction term that says, well, it's switched off outside some region. And maybe they differ only in the question of how big is that region, right? So one has allows for a bigger region than the other. These will give you consistent results on the Cauchy development of the smaller region. Essentially, that's the picture that comes out.
Oh. Okay. I guess Martino can tell us if he was satisfied with the question, with the answer. Yes, he says yes. So then we have Nick Haggett.
Hi. Yeah, thank you again. Like, that was really beautiful, and been trying to sort of think my head around some of these things, and that was really, really helpful. So I mean, just a couple of what I think are sort of maybe, small questions. So the first one's about the clarification of how to interpret an algebraic quantum field theory.
Yes.
And the question is, what about the non-self-adjoint elements of the algebra?
Yeah, I mean, that's you could raise that question in quantum mechanics as well. What about them? Well, they will represent, so at least the normal ones will represent functions of observables. Right. So there's no particular difference there. I guess the reason I say that I'm interpreting the self-adjoint ones is that normally we say we'll know how to measure something that's self-adjoint.
Yeah.
And one of the properties of this induced observable map is it respects the star. So if you measure a self-adjoint operator on the probe, the induced observable is something self-adjoint in the system. Okay, so this aspect of the interpretation is preserved. Actually, also, the same is true about gauge invariance. If you measure something gauge invariant in the probe and the coupling is gauge invariant, which can be expressed precisely, then you're measuring something gauge invariant in the system as well.
Okay, but this statement you wrote here, really, there was a sort of implied self-adjoint element. Is that right? Or
yes. Yes.
Okay.
Yes. Sorry, you're absolutely right. Yeah, maybe. Yeah, I should tighten the wording there. Yeah, the typical self-adjoint element should be interpreted as an observable, whereas the typical unitary element doesn't necessarily carry the interpretation of an operation implemented by local physics. That's the distinction I'm getting at.
Okay. So do you think this has some implication then for how to think about sort of Ray-Schlieder theorem and the sort of non-locality that's there?
That's interesting. I haven't. So in our original paper, we did briefly touch on the Ray-Schlieder theorem, but not quite in connection to this distinction. So I'd have to think about that a little bit.
Okay.
But hang on, but your question on Ray-Schlieder, that wasn't in relation to this distinction, though, was it? Were you just saying what's the relation with Ray-Schlieder?
I guess I don't fully understand how to think about the theorem, but it always seemed to me that there was something there about. It looks like it's a theorem about observables, but then gets treated as a theorem about sort of operations that you can perform, I guess.
Ah, yes, sort of behind the moon type things. Well, yes, that is interesting. Yes, actually, I think that would be correct, because the way this is done is to say that if you take local elements, if you take elements from any local algebra and let them act on the vacuum vector, in assuming that's got the Ray-Schlieder property, then this is dense in the Hilbert space. So you can effectively create any state in the Hilbert space to arbitrary approximation by acting with some local observable. Yes. So then the question is, how would you physically do that?
Yeah, yeah.
So, and that is something that is never specified in discussions of the Ray-Schlieder theorem. And I think that this perhaps goes all the way back to Haag and Kastler, because in their paper, interestingly, they take the view that the local algebras are algebras of local operations. That's what they say. And they actually say observables are much more complicated for reasons I never quite understood what they were driving at by saying that. And if you trace the history, it's quite interesting, because for the first couple of years, people say it's algebra of operations. And I think Haag does mention it in his book, again, Algebra of Operations. But within about 5 years, people are saying these are algebras of observables. So there was a sort of shift in opinion, but this wasn't based on any analysis of actual measurements. It was sort of a change in sentiment, perhaps. I think there'll be something interesting to do to dig into the reasons for why that shift occurred. But the distinction we're drawing is based on the observation that local elements, elements of local algebras can represent non-local operations, but self-adjoint elements can be measured by local physics. So
is it? Yes, that's, I guess, yeah, good. No, I think then that was sort of the idea, or maybe I had it inchoately in the back of my mind. Then might it be that the apparently local observables that allow you to produce the non-local effects actually correspond to non-local operations, and so it's not so mysterious what's going on?
That is entirely possible, because because I don't think you don't have an awful lot of control over which observables would produce for you the spaceship behind the moon. So I think it quite likely. Yeah. I haven't looked at that in detail, but I think that's a very interesting point.
Okay. Can I ask another question on it? I sort of had a little. If there are other people, I can go back in the line, but I don't know.
No, right now there's nobody with their hands raised. Okay. I have a question, but I will ask it last. Okay,
so since I'm here, and it was actually related to what Lucian's first question. So I don't like the thinking about all this just in knowledge terms. So I wanted to sort of suggest sort of an amendment along the similar kind that maybe would be still acceptable, or which is you're not really conditioning on sort of knowledge, you're actually conditioning on outcomes. So I can think of the outcomes as non-sort of epistemic, they're real physical, local beables in Bell's idea, and that's what so I could delete knowledge and just say outcomes instead.
Yes, this may have been. Yes, I mean exactly. The knowledge here should be outcome. I would agree with that quite happily. Yes, I'm not. This is not something psychological. It is about the outcome. Okay. Whether you select, I mean, to a certain extent, whether it's been selected on. Okay, so in order to make the selection, there may be some element of data processing, for example, from an ensemble of measurement results, but it could indeed just be a one-shot thing. We got a positive measurement from A, and therefore we update the state in order to make better predictions.
Okay. Yeah, no, that's helpful. So anyway, thanks again very much. This was real. I'm hoping to teach some of I'm a philosopher of physics, and I'm hoping to teach some of this in my seminar next semester. I'm definitely going to have
great.
The students watch this, because I think it's really
Well,
been very helpful for me.
Do feel free to get in touch if there are questions or comments.
Yeah, I've talked to Doreen Fraser a bit about this, who I think has been talking with you. So I think
that's right.
Yeah, it's very interesting. Anyway, thank you very much.
Pleasure.
We have one question in the chat. I don't know if the person who asked it wants to unmute themselves. Just ask it.
I can do that.
Yeah, it's nice.
I wanted to ask, I guess first I should say it was a really nice talk. Thank you so much.
Mm-hmm.
I wanted to say, you mentioned right on this slide actually that these states were just objects that we use to find measurement probabilities. But isn't that an assumption in itself? I'm thinking about here kind of maybe philosophically, but like what if the states are physical objects in themselves and then it's not just bookkeeping? But
yeah, okay, so that's a good point. So what I have done here is to essentially characterize them by their use. Okay, so this is certainly, in a sense, mathematically, all we have at our disposal is this probability rule. Okay, so that's the only thing that tells us anything about what the state is for. Right. And then if you take the view that, well, you're trying to produce updated predictions, you can compute what the updated state is. And now notice that what I said was it is not necessary to assume that the state actually changes. Okay. So this leaves open the question of whether or not the state is an actual physical object. But what I want to point out is you do not need to assume that it is. Everything is completely consistent with this bookkeeping idea. And therefore, I mean, of course, you can tell which way my sympathies are going, right? But on a sort of Occam's razor viewpoint, I'm not forced to assume that the state has physical reality in order to do what I'm doing here, and therefore my inclination is to take the minimal viewpoint. Okay, so nothing in what I've described to you today forces me to adopt the viewpoint that a state has physical existence, right? And it changes in a measurement. And there are all sorts of problems of trying to make that viewpoint work if you want to say that there is a transition in space-time across some hypersurface. And so because this was a short talk, I didn't put it in, but I often give an example by Aharonov and Albert, where they show that collapse across a hypersurface gives you conflict with charge conservation, for example. And this is something Rainer and I write about in our encyclopedia article, if you haven't come across that one. So I think it's a problematic viewpoint to hold when you've got relativity around, because there's no simultaneity anymore. And what's good about this framework, from my viewpoint, is you don't need to worry about it anymore, because you're not forced into a position that the state has some physical existence. So that's the viewpoint. But this is not a proof that the state has no physical existence. I know people write no-go theorems about that sort of thing, but that's not what this is. This is saying we can manage perfectly well without assuming that the state has real physical existence and collapses across hypersurfaces in space-time. So okay, if you like, it's no need of that hypothesis territory.
Thank you.
And we have one more raised hand.
Actually, I'm trying to follow this your answer, because I mean you said you don't have to update the state, but we can update state.
Oh, no. So what I'm saying, yes, we can update the state, The question is that a physical process that is happening in space-time, or is this a matter of us making essentially us as users of quantum field theory updating the state in order to compute post-measurement outcomes. Okay, so the state should be updated, definitely. The question is whether this is some sort of mathematical or bookkeeping exercise, or whether it is something that is physically happening in the universe, whether or not we care to notice it.
But either way, there's no contradiction, because either you update or if you consider state is epistemic or ontological, still there's no actually contradiction between two.
Exactly. That's why I write here, it's not necessary to assume that it changes. Okay.
So in measurement operator in the quantum field theory is different from ordinary quantum field theory, like projective operator.
No, I mean, I think everything that we do here is actually consistent with ordinary quantum mechanics. You can actually understand the Luder's rule, for example, as an example of this sort of update. It's just that I think very often this is forgotten in the presentation of quantum mechanical measurement. The Luder's rule applies to a very specific sort of measurement. It applies to an ideal repeatable measurement, right? So that statement that it's ideal and repeatable actually gives you a lot of information about the conditional probabilities, and it's enough to work out at least well, particularly if you've got non-degenerate eigenspaces, then you can really say we must now be in an eigenstate of the measurement operator. Yeah, I mean, so but that comes in because we claim that we have some knowledge about the post-measurement state, namely that it arose from an ideal repeatable measurement. So actually, ordinary what we teach to first or second year students, this can be understood from this viewpoint. And again, as I say, this is not an original view that I've come up with. It's been around for a very long time, but somehow a bit of a subculture. And again, an interesting question for historians and philosophers of science is where did that change? And maybe somebody knows the answer. I'd be interested.
Thank you very much.
All right, so I guess it's time for my question. And also my question is not really specifically about the framework that you presented, because I guess the presentation was so clear that it doesn't require further elaboration. But I have a question more generically on this operational understanding of the operators, of the algebra. And specifically is that, so especially now that you mentioned that that elements of the algebra, at least the self-adjoint ones, should be considered as possible observables. How do we think about the fact that it's an algebra, that there is a multiplication?
Yeah,
I've been asked this question a lot when I'm talking about quantum field theory, because
so,
obviously the product of two self-adjoint operators is not self-adjoint.
Yeah,
but somehow the algebra is important.
Yeah. So, I mean, you can do a certain amount, and then it gets difficult. So it's understandable what a scalar multiple of an observable means, right? You're just repainting the scale by multiplying everything by some constant. It's actually understandable what the sum means, because if we want the expectation value of the sum, it's the sum of the expectation values. So you can say, well, do both experiments independently and add up the results. So we understand that. Now, what about more general things? Well, the simplest thing you can do is consider the square of an observable. And this, again, is a matter of repainting the scale. So if you can measure some observable A with some range of outcomes, then you can certainly measure an observable that would deserve to be A squared. Okay, just change the scale. But we've already agreed that you can do sums.
Right.
So we also now know we have an a plus b squared.
Mhm.
Okay. And we know, we claim we understand what a squared and b squared are. So now that means that we have some sort of interpretation for AB plus BA, this the anti-commutator of two algebra elements. So there is a natural way into assuming that you at least have what's called a Jordan algebra, which is where you get this symmetrized product. To go from that to an algebra is where things get complicated, but there are books that and papers that do this, so it's something that's been studied. And I would perhaps refer you to a book by Emch. It's called, maybe I can, maybe I'll email you after the
Okay.
after the seminar. So it's over there, but I don't want to just sort of wander off.
Yeah.
even an online seminar we done. So, but yeah, there are certainly analyses of this question. You have to, of course, assume more. So the very simple ideas I gave you, I think, motivate. You go quite a long way towards the algebra. And one approach is just to be pragmatic and say, well, look, if we understand AB plus BA, or something that deserves to be called that, then why not just use the simplest mathematical object that will allow us to do that, which
Right.
would be an algebra. But then you can work harder with more assumptions, and then are led to the fact that only an algebra will allow you to have everything you want.
I see. Okay, so this has been studied.
Yeah.
Oh, somebody sent it. Algebraic methods in statistical mechanics.
Thank you very much. Yes, that's the one. Yeah.
Algebraic methods in statistical mechanics and quantum field theory.
Yeah.
Cool.
But it's quite an extended discussion, actually. So it's quite surprising. So in 30 seconds, I told you what sounds as though it's 3/4 of the problem, but in fact,
The last quarter.
Then the hard work starts.
That's great. So are there any further questions from the audience? All right. So in that case, please join me in thanking Chris again for the great presentation and the generous time for answering the questions.
Well, thank you very much indeed. It's been very interesting.
Yes. And yeah, see you all next year. Bye-bye.
Bye.
Thank you.